A new discovery may help answer the age-old question of whether or not we are alone in the universe.
Mystery widens. Today, people in the New York metro area are reporting a growing number of drone sightings.
The James Webb Space Telescope just captured images of Triton that stunned scientists. They show strange, glowing patterns on its icy surface that no one can explain. Now, these glowing signals could be proof of something hidden beneath its frozen layers. Or maybe it is something even more extraordinary that challenges everything we know about moons and planets. Let us uncover the truths that NASA might not be ready to share because it will mean the end of the government's existence. Triton's shimmering ice holds hidden clues. Triton's surface is a frozen wonderland covered in a reflective layer of nitrogen ice. This surface reflects most of the sunlight it receives, making it one of the brightest objects in our solar system. Despite its distant location, Triton's unique properties make it a prime candidate for exploration. Scientists believe that Neptune's gravity plays a crucial role in keeping Triton geologically active, with possible subsurface oceans warmed by gravitational forces. These oceans, hidden under miles of ice, are thought to hold the potential for life, a tantalizing prospect that the Webb telescope aims to investigate. Before we delve into this, it's clear that what the Webb telescope has uncovered on Triton is far more extraordinary than anyone dared to dream. And this won't be the only revelation to leave you speechless. What sets the James Webb telescope apart yet is its ability to see in the infrared spectrum. This capability allows it to peer through the icy exterior of moons and detect heat signatures, trace gases, and other hidden features. For instance, infrared light bouncing off a moon's surface can provide clues about its composition, revealing materials like methane, nitrogen, or even organic compounds. These observations could rewrite what we know about these icy worlds and their place in the solar system. The telescope's data collection is nothing short of revolutionary. By mapping temperature variations across a moon's surface, Webb can identify unusual hotspots that might indicate cryovolcanic activity or geothermal heat escaping from beneath the ice. Imagine discovering a warm, active spot on a moon thought to be frozen solid. Such a find could hint at hidden oceans and point to geothermal activity, a critical factor in the search for extraterrestrial life. Cryovolcanoes, which spew icy water and gases instead of molten rock, are a possibility, and Webb's instruments are equipped to detect their telltale signs. A thin atmosphere, mostly nitrogen with traces of methane, is another area of interest. The telescope's advanced instruments can analyze the composition and behavior of such atmospheres, providing insight into their interaction with the moon's surface and the broader environment. This knowledge could help scientists understand how atmospheres evolve on icy moons and what role they play in sustaining potential life. Webb's instruments, such as its near-infrared camera and mid-infrared instrument, are tailor-made for studying distant, faint objects. NIRCam can map a moon's surface by analyzing reflected light, while MIRI focuses on detecting faint heat emissions. Together, these tools allow scientists to study composition, temperature, and atmospheric conditions in unparalleled detail. For example, Webb might detect methane ice deposits, which could be remnants of cryovolcanic activity or collisions with other celestial bodies. One of the most intriguing possibilities is the existence of a subsurface ocean beneath an icy crust. Such an ocean, kept liquid by gravitational forces, could harbor conditions favorable for life. While Webb cannot directly observe this hidden ocean, it can detect surface anomalies that suggest its presence. For instance, a warm spot on the surface could indicate water seeping up from below, hinting at dynamic processes beneath the ice. If confirmed, this finding would make such moons among the most exciting targets for future exploration. The potential for habitability on icy moons raises broader questions about others in our solar system. Europa and Enceladus, moons of Jupiter and Saturn respectively, are also thought to have subsurface oceans. By studying these worlds, scientists hope to draw comparisons and better understand the conditions necessary for life to exist on these remote worlds. If their oceans contain organic molecules or show signs of chemical activity, it could provide clues about how life might arise elsewhere in the universe. Webb's observations could also shed light on geological history. A moon's surface marked by features like ridges, valleys, and possible cryovolcanic flows suggests a dynamic past. By analyzing these formations, scientists can piece together the events that shaped its surface. Did it experience massive collisions with asteroids or comets? Were there periods of intense volcanic activity? These questions are critical to understanding its evolution in place of an image solar system. Another exciting aspect of Webb's mission is its ability to detect trace gases in thin atmospheres. Gases like methane and carbon monoxide could be byproducts of geological or biological processes. For instance, the presence of methane could indicate ongoing cryovolcanic activity where water and gases are ejected from below the surface. Alternatively, these gases might result from chemical reactions within a subsurface ocean. Either way, their detection would be a groundbreaking discovery. What we've learned about Triton shows how much we can discover from far away. The search for life among the icy moons. Despite its capabilities, Webb's observations come with challenges. The vast distance from Earth, over 2 billion miles, makes it difficult to capture high-resolution images. Additionally, the faint light reflected from icy surfaces requires long exposure times, limiting the telescope's ability to observe rapid changes. However, these limitations are a small price to pay for the wealth of information Webb can provide. The data collected by Webb will serve as a foundation for future missions. Scientists are already envisioning orbiters and landers that could follow up on Webb's findings. An orbiter could map surfaces in high resolution, study atmospheres in detail, and confirm the presence of cryovolcanic activity. A lander, on the other hand, could analyze surface samples, search for signs of water or organic molecules, and provide direct measurements of geology. Balancing the desire for exploration with the need to protect these environments from contamination is another critical consideration. Any mission must ensure that Earth-based organisms do not inadvertently hitch a ride and compromise these pristine environments. At the same time, scientists must develop methods to distinguish between Earth-derived contaminants and potential signs of extraterrestrial life. This delicate balance will be essential as we continue our exploration of the outer solar system. Connections to the Kyper Belt, a region of icy bodies beyond Neptune, add another layer of intrigue. Some scientists believe that certain moons were once Kyper Belt objects captured by gravity. If true, studying them could provide insights into the origins and evolution of other Kyper Belt objects, including Pluto. Webb's ability to analyze composition and geological features could help confirm this theory and deepen our understanding of the solar system's early history. The implications of Webb's findings extend far beyond individual moons. By revealing their questions, the telescope could reshape our understanding of icy worlds across the solar system. It might even help us answer fundamental questions about the conditions necessary for life. If any of these moons prove to be geologically active or host subsurface oceans, they would join the ranks of Europa and Enceladus as prime targets in the search for extraterrestrial life. As we wait to hear about what Webb's observations reveal, the excitement grows stronger, and it's hard not to feel amazed at what might come next. Triton, once a distant and strange place that felt almost like a question we couldn't answer, is now becoming a central focus in how we try to understand the universe better. The James Webb Space Telescope, with its incredible tools and unmatched abilities, is helping us see things in a way we never could before. It's not just looking at Triton, it's helping us open the door to a whole new way of exploring the wonders of our solar system. The things it might uncover could completely change what we think we know about Triton and spark a whole new wave of interest in the search for life beyond Earth. The more we learn from these observations, the more surprises we might uncover about the outer reaches of our solar system. Every bit of information Webb collects adds to a bigger picture, showing us how moons, planets, and even the faraway Kyper Belt all connect and influence one another. Triton, with its shiny surface made of frozen nitrogen and the possibility of hidden oceans beneath its icy crust, stands out as a perfect example of what could be possible in other unexplored worlds. Imagine what we might learn if we could someday visit moons or planets with similar conditions. It's an idea that makes you think about how much more there is to discover. As technology keeps improving, everything Webb finds will serve as a solid foundation for future missions. inspiring us to aim even higher in space exploration. Triton's potential as a unique world can't be ignored. Its surface reflects light like a bright beacon in the dark reaches of space, and scientists think it might hold underground oceans that could tell us more about where life might exist. These possibilities make Triton a place we can't overlook. The James Webb Space Telescope is not just a tool, it's like a guiding light that helps us take our first steps toward understanding these far-off places. Each observation it sends back is like adding a piece to an enormous problem that shows how our solar system is connected. From Triton's icy world to the search across our solar system, people have always wanted to go beyond what they already know. Unveiling the origins of planets and moons. The history of exploring the solar system is a story packed with ambition, trial, and awe-inspiring discoveries. For thousands of years, people gazed at the stars, dreaming about what might lie beyond Earth. Then in just the last century, we found ways to break free from our planet and start visiting the vast expanse of our solar system. Each new spacecraft sent out has unraveled more about the planets, moons, and even tiny celestial rocks that orbit the sun alongside Earth. The first steps into this exciting era happened in the late 1950s. In 1957, the Soviet Union sent Sputnik 1 into orbit, marking the start of the space age. This shiny little satellite might have been basic compared to today's standards, but it made history as the first human-made object to circle the Earth. It wasn't long before both the United States and the Soviet Union began aiming higher, literally setting their sights on the moon. At first, these efforts were riddled with failure as rockets exploded, missed their targets, or simply stopped working. But even those setbacks helped scientists figure out how to make future missions work better. By the early 1960s, things began to take off, literally. NASA's Mariner 2, launched in 1962, flew past Venus, sending back data about its hot, thick atmosphere. That mission was a big deal because it showed that we could successfully send a spacecraft to study other planets up close. Just 3 years later, Mariner 4 gave us the first images of Mars, a barren, dusty world that looked nothing like the lush alien planet some had imagined. Each success made us bolder, and soon the race to explore was in full swing. The moon became a major focus during the 1960s. The Soviet Union's Luna mission set several milestones, including the first crash landing on the moon in 1959 and the first soft landing in 1966. But it was the United States that captured the world's attention in 1969 when the Apollo 11 mission landed humans on the moon for the first time. Neil Armstrong and Buzz Aldrin walked on its dusty surface, leaving footprints that would become iconic symbols of human achievement. Over the next few years, 5 more Apollo missions landed on the moon, bringing back rocks and learning more about its ancient surface. By the 1970s, the exploration expanded beyond the moon. NASA's Pioneer 10, launched in 1972, became the first spacecraft to travel through the asteroid belt and reach Jupiter. It sent back stunning images of the giant planet's swirling storms and its many moons. Pioneer 11 followed, not just studying Jupiter, but also giving humanity its first close look at Saturn in 1979. These missions set the stage for even more ambitious explorations. The Voyager missions, launched in 1977, were nothing short of groundbreaking. Voyager 1 and 2 explored Jupiter and Saturn in incredible detail, uncovering volcanic activity on Jupiter's moon Io and the delicate structure of Saturn's rings. Voyager 2 went even further, becoming the first spacecraft to visit Uranus and Neptune. It sent back images of Neptune's deep blue atmosphere and Uranus's oddly tilted magnetic field, showing us just how unique these far-off worlds are. In the 1990s, our attention returned to Jupiter with the Galileo spacecraft. Galileo not only studied the planet's massive storms and magnetic field, but also discovered something shocking: subsurface oceans on its moons, Europa and Ganymede. These findings raised the exciting possibility that these moons might host life beneath their icy surfaces. Around the same time, the Hubble Space Telescope, though not a spacecraft visiting planets, gave us detailed views of the solar system and beyond from Earth's orbit, revolutionizing how we see the universe. Then came the Cassini mission, launched in 1997. When it reached Saturn in 2004, it gave us breathtaking views of the planet, its rings, and its many moons. The Huygens probe, part of the Cassini mission, landed on Titan, Saturn's largest moon, in 2005. Titan turned out to have lakes and rivers, not of water, but of liquid methane and ethane, making it one of the strangest landscapes we've ever seen. Cassini continued to orbit Saturn for over a decade, providing more data than scientists could have hoped for. Mars was a hot topic again in the late 1990s. The Mars Pathfinder mission, launched in 1997, delivered a small rover named Sojourner to the Martian surface. This was just the beginning of robotic exploration on Mars. The twin rovers, Spirit and Opportunity, landed in 2004, finding evidence that water once flowed on the planet. Later, the Curiosity rover, which landed in 2012, dug even deeper, literally into Mars's history, studying its rocks, climate, and potential for past life. Smaller celestial bodies weren't ignored either. In 2001, the Near-Shoemaker spacecraft landed on the asteroid Eros, sending back close-up images and data about its composition. Later, the Dawn mission explored the giant asteroid Vesta and the dwarf planet Ceres, two of the oldest objects in the solar system. These studies gave scientists a glimpse into the building blocks of planets. The 2000s brought even more international collaboration. The European Space Agency's Rosetta mission, launched in 2004, became the first to orbit and land a probe on a comet. The mission's landing on Comet 67P in 2014 was risky and dramatic, but it succeeded, giving us an up-close look at the icy body's composition. Comets, with their ancient materials, offer clues about the early solar system. Meanwhile, NASA's New Horizons spacecraft, launched in 2006, made history by flying past Pluto in 2015. For decades, Pluto had been little more than a distant dot in telescopes. But New Horizons showed it to be a dynamic world with towering mountains, icy plains, and a surprisingly complex surface. The spacecraft didn't stop there. It continued deeper into the Kyper Belt, exploring even smaller, ancient objects on the solar system's edge. Jupiter got more attention in 2016 with the arrival of the Juno spacecraft. Juno has been studying the planet's atmosphere, gravity, and magnetic field, giving us new insights into how gas giants form and evolve. Its detailed data has shown us just how turbulent and strange Jupiter's interior really is. The big steps we've made in space exploration are now leading us to think about something even greater: building a new world on the red planet. The idea of humans settling on Mars feels like something straight out of a movie, but it's more than just fantasy. For decades, scientists, dreamers, and billionaires have poured time and money into figuring out how to get us there and keep us alive on the red planet. Why Mars, though? It's not exactly a tropical getaway. The temperatures are freezing, the air is poisonous, and it's bombarded by cosmic radiation. Yet people can't stop imagining what it would take to build a new world there. Mars is relatively close to Earth compared to other planets, and it has some features that remind us of home. There's evidence of water in the form of ice, which is a big deal for survival. It has seasons, polar ice caps, and even the potential for resources hidden beneath its dusty surface. But don't let that fool you. It's a dangerous, barren place. Still, the dream persists, driven by a mix of survival instincts, scientific curiosity, and the need to push boundaries. One of the main reasons people are so fixated on Mars is survival. Let's face it, Earth isn't doing so great. Between climate change, natural disasters, and other existential threats, having a backup planet starts to sound like a smart idea. If humanity could build a self-sustaining colony on Mars, it could serve as an insurance policy for our species. But it's not just about escaping Earth's problems. There's also the thrill of discovery, imagining what we might learn by studying Mars up close. Could there have been life there? Could there still be life? The answers could reshape how we see the universe and ourselves. Of course, none of this comes without a mountain of challenges. Getting to Mars is a feat in itself. It's not like hopping on a plane. We're talking about a path of around 140 million miles. Even with the best technology we have today, it would take about 6 to 9 months to get there. During that time, astronauts would be stuck in a cramped spacecraft, facing isolation, microgravity, and the constant risk of something going horribly wrong. Once they arrive, they'd have to deal with Mars's thin atmosphere, extreme temperatures, and high levels of radiation. And that's just scratching the surface. The environment on Mars is nothing like Earth. The atmosphere is mostly carbon dioxide, so forget about breathing without a spacesuit. Temperatures can plummet to below -70 degrees Celsius, and the planet lacks a magnetic field to shield against cosmic rays. Add in the fine, potentially toxic Martian dust that can infiltrate equipment and lungs, and you've got a recipe for disaster. Despite these risks, scientists and engineers are coming up with ways to make it work. The focus is on creating habitats that can shield humans from radiation, recycling water and air, and finding ways to grow food. Building a colony on Mars would mean relying on local resources as much as possible. Shipping everything from Earth would be insanely expensive and impractical. That's where in situ resource utilization comes in. This fancy term means using what Mars already has to support human life. For example, scientists are working on ways to extract water from the soil and convert the planet's carbon dioxide-rich atmosphere into oxygen. These innovations are crucial for survival and could also pave the way for long-term living on Mars. But let's not forget the human side of things. Spending years away from Earth, living in confined spaces with limited communication and no chance of stepping outside without a suit will take a toll on mental health. Astronauts would face isolation, boredom, and the constant stress of knowing that one mistake could be fatal. Maintaining their well-being would require more than just good tech. Recreational activities, meaningful work, and a sense of community would be essential to keep everyone sane. Despite all this progress, it's clear that colonizing Mars won't be easy. The technical, physical, and psychological challenges are immense, and the costs are astronomical. But the potential rewards, survival, discovery, and the chance to build something entirely new, keep the dream alive. Whether Mars becomes humanity's second home or remains an unattainable goal, the path to get there is already pushing the boundaries of what's possible. For now, we can only imagine what it would be like to stand on the red planet, looking back at Earth, knowing we've taken the first steps toward a future beyond our homeworld. Could these glowing patterns on Triton be natural phenomena? Or is there evidence of something extraterrestrial that NASA won't admit? Share your thoughts and don't forget to like and subscribe for more.